Across medical education and clinical instruction, generative AI now produces drafts in seconds that previously required hours of human synthesis. These systems generate material at scale, yet they lack the cognitive architecture to assume professional accountability for the accuracy of their output. Within this environment, faculty remain legally and ethically responsible for clinical accuracy, assessment fairness, and the protection of patient privacy. Managing this institutional risk requires a systematic framework for every tool we integrate into our workflow. The necessary level of human oversight is determined by a tool's underlying mathematical architecture. We must distinguish between two technical categories: deterministic software and probabilistic models. This distinction allows faculty to utilize AI while maintaining the institutional safety standards required in clinical and scholarly practice. The professional decision matrix serves as our master framework for evaluating the safety of any AI-assisted workflow. The first row contains Category A tools, defined as embedded utilities and analytics. These systems utilize deterministic machine learning, meaning they operate on explicit parameters and host platform rules. Common examples include EHR search indices and the proofreading tools within Microsoft Word. Their primary functions are to correct style, format bibliographies, or extract specific parameters from structured data. Because they do not generate original narrative text, Category A tools carry zero fabrication risk. As this flowchart illustrates, these tools only retrieve or organize existing data. They are not programmed to invent new narrative facts. Therefore, the required faculty action is a standard review, verifying the output for readability and tone. Since their architecture restricts them from inventing medical data, deterministic tools fit within our standard proofreading workflows. The second row of the matrix covers Category B, generative large language models, such as ChatGPT or Copilot. These platforms require open-ended prompts to synthesize entirely new clinical or educational materials. At a technical level, a large language model is a probabilistic algorithm. The system operates by calculating the statistical probability for the most likely next word in a sequence. This means LLMs are not verified databases. They do not retrieve stored facts from a library of medical truth. Faculty use these tools for high-value tasks, drafting clinical vignettes, creating grading rubrics, or summarizing research. While Category A tools focus on formatting, LLMs generate entirely new narrative structures and reasoning chains. Because every word is a mathematical prediction rather than a retrieved fact, the LLM architecture introduces a structural risk to clinical accuracy. This structural risk manifests as a hallucination, where the model generates a factual fabrication. The model may generate a false lab value simply because that specific number has a high statistical probability in its training data, regardless of the empirical medical reality. These fabrications are difficult to spot because the model presents them with absolute confidence and plausible clinical formatting. LLMs will frequently invent peer-reviewed citations, patient values, and clinical guidelines that do not exist. To counter this risk, the mandatory faculty action for all generative AI output is a rigorous manual audit. This requires that every citation, reasoning chain, and clinical value be independently fact-checked prior to use. This audit is a distinct process from the standard proofreading review used for deterministic software. Using AI moves the faculty's primary effort from the initial drafting of content to its verification. To safely integrate these models, faculty must transition from being primary content authors to being rigorous medical auditors. Beyond the accuracy of the output, we must also consider the legal implications of what we input into these models. There is a zero-tolerance boundary regarding the types of data that can be submitted to public probabilistic models. This includes HIPAA-protected patient details, controlled unclassified information, or CUI, and confidential student records. Entering protected data into external models constitutes an immediate breach of institutional policy. We only use generic prompts and public knowledge. Inputs containing real patient variables are strictly quarantined. Generative systems can simulate clinical scenarios, but they cannot legally process real ones. Protecting patient privacy and CUI is a non-negotiable requirement that supersedes any workflow efficiency gained by the tool. This framework provides a consistent method for evaluating any new software against our institutional risk. Our responsibility is dictated by the math. The tool's architecture determines the intensity of the human audit required. We must apply structured verification to catch plausible fabrications in medical content. We must maintain a strict quarantine of all HIPAA and CUI data from generative inputs. We will adapt our assessments to ensure they measure authentic reasoning in an AI-accessible environment. And we must establish clear authorship boundaries and disclose AI utilization in medical scholarship. Artificial intelligence can produce medical content at a volume humans cannot match, but it cannot assume the professional accountability that content requires. The faculty member remains the ultimate guarantor of truth.